We have looked at three reactions of turning an alkene into an alcohol, with the first reaction reacting the alkene under acidic conditions to form a Markovnikov alcohol that's open to rearrangement. Next, we look at hydroboration and oxidation to put a hydroxyl group on the least substituted carbon. For a third example, we looked at oxymercuration demercuration, which provided us a tool to prevent carbocation rearrangement by avoiding the formation of a carbocation intermediate. Following, we then learn how to take the double bond or the alkene into a new functional group, or the epoxide, bridging an oxygen between the two double bond carbons through reacting with a peroxide. With this new reaction, we're going to put a lot of things together as we form a diol, or put a hydroxyl group on both of the double bond carbons. In a process called dihydroxylation, we'll react our now formed epoxide under acidic conditions to form an oxonium ion that gets attacked by water to form our diol product. Dihydroxylation, by reacting an epoxide under acidic conditions, puts the hydroxyl groups on the double bond carbons on opposing sides spatially, or an anti-addition process. Let's look at an example to just see why this reaction results in an anti-addition process. We'll first form our epoxide that will then react in acidic conditions to protonate the epoxide oxygen. This intermediate resembles intermediates that we've seen in reactions prior, such as halohydrin formation and oxymercuration demercuration, when in both of those cases, the incoming nucleophile attacked the more substituted carbon of the structure from the opposing side. So our reaction continues as water attacks a more substituted carbon, gets deprotonated by a neighboring water molecule, and we're left with our diol product. Let's summarize how we can take an alkene to a diol through first forming an epoxide. We'll react the alkene with MCPPA that will form our epoxide product. Then react it under acidic conditions in which we'll protonate the epoxide oxygen, forming a cyclic oxonium ion that gets attacked in an anti-addition fashion by a water molecule in solution. That through deprotonation, we are then left with our diol product and its enantiomer throughout the reaction.